Professor Zdeborová is with PERCEPTRON. Her work, especially in connecting physics with machine learning and statistics, has been extremely influential in our community. She has been awarded many awards. I'll be very brief and just list two. This includes the CNRS Bronze Medal and the Irene Joliot-Curie Prize. And today, Lenka Zdeborová will tell us about the role of data structure in learning shallow neural networks. Lenka, take it away. The stage is yours.
So yeah, thank you, Afonso, for the great intro. So I actually have three affiliations: Paris SECLA, CNRS, CA SECLA. But soon the campus of PPFL that you have just seen on the next venue for MSML. So that's kind of correlated with the fact that we will be organized. But to the science now. So I want to be, so when I'm thinking, oh, so my arrows are not working. Why is that so? Okay, now they're working. Okay, sorry. So when I'm thinking about how to proceed towards a theory of supervised deep learning that would be able, say, to predict which algorithm and which architecture we should use for a given data set, I really think of the three kind of facets of learning: the choice of the architecture, the choice of the algorithm, and we have seen, for instance, in Wijnand's talks, the kind of concept of implicit regularization, that the algorithm has something special to it that makes the whole process work. In Stefan Mala's talk, we have seen a beautiful discussion about the role of the architecture as a kind of a prior that makes it work. But there is the third side that is about the data itself and the structure in the data. And that side is discussed maybe less often so that's the one on which I will concentrate today. Of course, why we need to concentrate on that side as well is kind of captured in this slide. Because if we think of approximation theory, we might think that, for basically all data, the neural networks can represent any reasonable function. And these are, results of approximation theory that also Wijnand reviewed. So that's the good news. Now, if we go to computer science, the bad news is that if we look at the worst case data, so we, in the literature, there are examples of what that means, but in the worst case, the learning would be NP hard. So even though there exists a neural network that approximates the corresponding function, in the worst case, it's computationally prohibitive. Yet we are seeing in the third bullet, the empirical machine learning on the benchmark dataset that you all know is working great. And so on those data sets, learning is tractable. So there is this question lurking: what is the property of data that makes learning tractable? So what makes the data we are interested in different from the worst case in which it would not be tractable? So there is a fourth bullet, or fourth, say, a field that was looking at that question for a long time, and that's statistical physics. And the approach to this question of how to look at the structure of the data in learning is the physics one. We cook up a solvable model of learning and then try to understand and get insights from that. So the very classical solvable model of learning that have been studied in statistical physics is this teacher-student neural network. So that's actually exactly the same setting that, for instance, Wijnand was doing his experiments on. That's when the input data X would just be IID Gaussians. So not only IID sample from sample, but also the component from component. And then the labels would be created by some teacher neural network, in the simplest case, just this single layer neural network given by nonlinearity on the scalar product of some teacher weights and the data. And there has been, here I'm listing just some highlights of papers. There has been hundreds of papers on this kind of setting in the statistical physics literature, with the first one going back 30 years ago by Gardner and Derrida, where they actually introduced this teacher-student model and studied it in the limit that at that time in statistics was in a very baby state, the high dimensional limit, when the number of dimensions, p, is large, and the number of samples is large as well, but proportionally to the number of dimensions. So not much larger than the dimension. So that, you know, as most of you know, it's kind of a challenging limit to look at in statistics. And in this limit, they actually could back then, 30 years ago, solve this, this model in the sense that they computed what is the information theoretically optimal generalization error that any algorithm can possibly achieve in this model. And this has been, for instance, in the work of Geza-Georgi for the case where the teacher weights, so the weights of the teacher network, are binary, ±1. And the graph here is showing the generalization error as a function of the ratio between the number of samples and the dimension. And both dimension and number of samples are large. That's the limit in which this result is obtained. And you see that the generalization error has a sharp drop from something quite bad to 0. So there is a phase transition. That's also what makes the physics people so interested in these models. So jumping 30 years forward, the kind of current state of the art on this particular model, that also in statistics could be just called the generalized linear model with a, with data generated by a teacher, is in our paper a few years back, where we not only prove that the results from 30 years ago that were obtained with rigorous methods actually are correct, and we also link the optimal performance with the performance of approximate message passing algorithm and generalize to any activations and any prior on the way. So before showing you some of those results, let me just note what I mean here by the optimal performance on the generalization error that no algorithm can beat. So it's not what we are usually doing in machine learning. The empirical risk minimization is just one mean to get to something good. But if we actually know how the data were generated, like in this model, then the procedure we should follow to get the best possible generalization error is the following. We should look at the posterior probability distribution of what were the ground truth values of the weights of the teacher. And instead of getting the most likely value of them, we should be taking the network that is learning and averaging the weights of the network over that posterior. So do this kind of marginalization of that. So that's the procedure that we need to analyze to know what is the best generalization error that no algorithm can possibly beat. And if we do that, and that's what we did in that paper a few years back, for instance, for the case where the teacher weights are Gaussian and the labels are generated with a sign, nonlinearity, then this is a classification problem, would be called the spherical perceptron in the statistical physics literature. And here I'm plotting the optimal generalization error in red as a function, again, of this ratio between number of samples and the dimension. And in black is the performance of the approximate message passing algorithm that is, the theory predicts should be lying on the red line in this case, so you see it does. And the blue, there will be just out of the box performance of logistic regression taken from scikit-learn. So you see in this case is very, very close to the optimal one. So if it was always like that our job, would be very easy, like the black box standard procedure is close to the optimal, but it's not always like that. So if I go back to this case where the weights are binary of the teacher, and I learn again standard classification problem. So the red curve would be the optimal performance that no even exponential algorithm can beat. The green line is the analysis of the approximate message passing algorithm. You see that there is a gap between the two. So that gap actually is believed to be algorithmically hard in some very fundamental sense, but that could be for another talk. But for the purpose of this talk, I'm more interested in the blue line or points. That's again the logistic regression that is not picking this phase transition. Well, at the same time, it doesn't know that the teacher weights were binary, so it's not able from so few samples to discover that or learn that information. And a third example would be, you could think that these are kind of special things of classification with maybe discrete weights. So not at all. This is a case of phase retrieval. That's a standard regression problem. You can think about it as a regression problem. where the teacher weights are again Gaussian, so something continuous. The tricks is not in the complication on the prior. There's some prior information that I'm not giving the neural network. And here as well, we see a phase transition as the number of samples is increasing for the approximate message passing in blue and for the information theoretic performance in orange. And here, if I compare to what gradient descent would be doing, so just note that here the generalization error drops to 0 at about, you need few more samples than the dimension, maybe 1.13 times more samples than the dimension. If I try to solve the same problem with gradient descent on the straightforward loss that you would choose for this problem, then these are just numerical simulations from a recent paper by our group. You see that you need quite few more samples than what the approximate message passing algorithm would be needing, maybe 6 times or 7 times more times the dimension. And analyzing this, we have some approximate theory for that, but exact results for the gradient descent are still challenging, even in this simple case. So we can also, and again, in the statistical physics literature 30 years ago, there have been papers where you kind of have the same kind of fine-grained analysis with hidden units. Again, I need to specify the limit. So we are still in the high dimension limit of number of samples proportional by some constant to the dimension. And the number of hidden units will stay of order 1 for the analysis to go through. So I will call K the number of hidden units here. And then the hidden units, they can be organized in several layers if you want, but they can only be few of them so that this analysis goes through. And this is something that we have looked back at 2 years ago in this NeurIPS paper, where again, we analyzed the approximate message passing performance and proved that the replica formulas from 30 years ago are actually the correct ones for this model. And here's just one slide on what's the kind of result you can get if you start adding hidden units. So this is just the simplest possible case when you just have 2 hidden units. And then the teacher generates the labels following the function here. And then you're trying to learn that rule back using the same neural network, which is the thing that you should be doing from the base optimal point of view. And the plot is showing you, the black line is the generalization error that actually think interesting happening here at alpha equal 2 that is not so much visible in the value of the generalization error itself, but it's visible in some other kinds of order parameters that pop out in the analysis, that is interpreted in the following way, that if you have fewer samples than this critical value alpha, then you cannot do better algorithm, or even information theoretically, than just doing linear regression. And only if you have more samples than that critical value, then using hidden layers is actually, hidden units is actually giving you some advantage. So this is something that is in some sense observed in practice, that deep learning is useful only if you have a lot of samples. So this is a nice model where you can put some very concrete analysis on this specialization transition, we call this phenomenon. So coming back to the triangle of how these 3 facets of deep learning interact, there should be always emphasis on the algorithm. And so far, I was telling you more about this class of approximate message passing algorithms because they are very tightly linked to the information theoretic analysis. But in practice, we use more gradient descent or stochastic gradient descent. So we would like to understand how those actually perform. And this is something that I won't be talking about today, but we have been progressing quite well in this question on the class of models that I was describing. And this will be just a list of references where currently, basically for gradient descent, for one pass stochastic gradient descent, but also for multi-pass stochastic gradient descent, in the high dimensional limit and in the presence of non-convexities and spurious minima, we can actually write closed formulas for how does the learning trajectory look like as a function of learning time. And from that, in these papers, get some insight about how the dynamics is behaving. But the side I want to concentrate more about today is the side of structured data. So just to go back to this slide that I showed at the beginning, about the setting that has been definitely in the statistical physics literature studied quite actively for 30 years, where the input data X were just IID Gaussian noise. So no pictures, no correlations, no, say, symmetries to use convolutions, nothing like that in there. So that looks a bit limited. We would like to understand, our path forward would be to, in a similar sense, have solvable models for data, but that are closer to realistic data sets. And this is a research program that we kind of started a few years back, and so far resulted in these 3 works that here I'm referencing for your convenience if you want to go back to them. So, so how do we build such a better, more realistic model? So here we get inspired basically by the state of the art in machine learning, where we know that with generative neural networks, we can generate faces that are basically undistinguishable from real people faces. So if we dig a little bit of how this generator in a GAN that does that looks like, well, it's a feed-forward neural network that into which you feed noise and it outputs this picture. And the layer in which you feed noise is typically much smaller than the output layer, the number of pixels of the picture that you're generating. So what this is saying is that you basically found a lower dimensional representation of how faces look like, where the lower dimension would correspond to the dimension of this input layer into which you're just feeding noise. And so in a sense, it would mean that if you look at the input space, then the subspace that contains images of faces lies on some lower dimensional manifold in that input space that is kind of illustrated in this figure. And things like variational autoencoders would be doing something very similar, where the low dimension would be the bottleneck. So with this in mind, we thought, okay, let's try to mimic that and create a model that would A, mimic that, and B, be still in the class that we can solve with the same kind of a precision we did for the models I was presenting at the beginning. And we call that the hidden manifold model. So the idea is there that we take the input space, we pick a latent dimension that will be the dimension of the manifold on which the data will lie. And the coordinates of that manifold are represented by matrix F. Then on that manifold, we take coordinates of the data points that will be represented by matrix C. And then, well, one thing is that now we need to generate the labels. So in that lower dimensional representations, the classes should be kind of nicely divisible. So we actually do generate the labels based on the coefficients in this low dimensional representation by a teacher neural network that will be some function G on the coefficient C generating the labels Y. And then to generate the input data, we actually, in a sense, fold or distort this manifold by applying a nonlinear function sigma on the product of F and C. And this will be the resulting data set. So then for the learning, what you see is the labels Y and the inputs X generated this way, but the algorithm that is trying to learn that rule sees Y as in the usual sense, or as in the usual case. So this, this is just an idea, why not? But the kind of what makes it nice are 2 things. One thing is that this generating data this way reproduces some properties of learning that we observe on real data, and I will show you in the next 2 slides. And second, this type of data, we still can apply the same methodology and the same, it's some work, but we can solve it and compute the generalization error up, including the constants. So what are the things that we reproduce from learning on real data? So here is just a simple example of MNIST, because the neural network that we are able to analyze so far is just this one with few hidden units, the committee machine. So this will not be able to learn in any nice way, something like ImageNet. But on MNIST, even such a simple network is doing pretty well. So that's why I'm showing here an example on such a simple data set. And comparing it to how the learning curves, so the error as a function of how many samples I have seen look like for the hidden manifold model, as the number of hidden units, the K, is increasing. And you see here kind of the phenomenology that first you learn like linear regression, and as you're adding hidden units, you learn better and better, kind of more complicated function. So this is one thing, but the thing that is more interesting is that if you now take two different students, so two different learnings that differ in just one thing, and that's the seed of the initial condition. So you just initialize them independently at random, but otherwise all the parameters are the same, and you just train here with gradient descent or stochastic gradient descent, I mean, either. So what you see when, so first of all, again, you're learning quite well. It's a simple data set, it's a simple network. So that will be the generalization error is the blue here. On the test set, these two students will agree quite often because you learned well. So on the test set, you will agree, and that's they will agree, and that's the orange curve. And the green one, that's if you actually compare these two students, not on the test set, but on random Gaussian noise. And you see that they don't agree. They basically randomly disagree, just like in half cases they agree. So this is binary classification. So that's just randomly disagreeing. So this is interesting because this is telling you that the two independent students, why they figured out pretty much which digits of MNIST are odd and which are even, they did that while learning completely different function out of the submanifold. So now if you think in terms of like approximation theory of really approximating the same on the whole input space, how do you explain that? So I will not be answering that, but this type of phenomenon, having it reproduced in the MAL, is something that we find very interesting. So that was the first point, that it reproduces some interesting behavior of what that you see on real data. And now the second point, how do we solve this MAL? How do we compute the very tight generalization curves? So that again is building on past work, and here I just give a few of them, where for least square regression and max margin regression, there has been recent work by Montanari's group that analyzed random feature learning, but I will show you that that's very related. So the math in there was very related to what we are doing. And we generalized, so we at the same time as them kind of did this, analyzed the stochastic gradient descent, so the one pass stochastic gradient descent, and later on generalized to the matrix F that describes the manifold that is generic, and also for convex losses in this paper. So I will show you about this paper. So what's the setting here? So the data are generated as before from the hidden manifold, and the learning process that we will be analyzing here is ridge regularized regression with a loss that is not only square loss but generic loss. So for some of the results it needs to be convex, but not for all of them. So that's the setting. And now what kind of makes this setting analyzable is this Gaussian equivalence property. So that's something that we first observe kind of heuristically that holds, and then in the paper cited down here with crucial key contribution of our colleague Galen Reeves, we proved that this actually works in the limit that I'm stating here. So when the latent dimension and the ambient dimension of the manifold of the input space both go to infinity, the number of samples also go to infinity, but the respective ratios between these three are fixed to some constant. So in this limit, we can show that the learning curve on the hidden manifold MAL data is the same curve as if we actually generated the data without the nonlinearity sigma, and just with some scaling factors, kappa 1 and kappa star. So as if we generated the data, just product of the two matrices plus noise, plus identity with some constant factors, kappa 1, kappa star, and kappa 0 that are here the F and sigma are actually, in this slide, are actually the same function. I just forgot to change the F to sigma. So this Gaussian equivalence is kind of key for the analysis then to go through. And if you go through the analysis to state what is the closed formula for the generalization error, it's kind of non-intuitive. So that's the formula. It's a set of fixed point equations that you need to solve and plug them then in the formula for the generalization error that is given down here. So the key here is that this is just one-dimensional set of equations. All the other parameters here are scalars. The dimensions and the number of samples that were large, they went to infinity, and this formula is already in that limit. So we got rid of the high dimensionality. And then, okay, then it looks a little bit bulky. So those of you who have seen how the replica formulas look like, you will recognize the kind of generic form, but otherwise this will be non-intuitive to you. But it's a formula where the loss function enters here, and the only way the matrix F that describes the coordinates of the submanifold enters is through its Stieltjes transform, and otherwise that matrix doesn't need to be random. That can be completely deterministic matrix with some kind of balance conditions, not completely arbitrary one, but very generic one. And finally, the nonlinearity that you apply to generate the data enters through these coefficients kappa 0, kappa 1, and kappa star that already entered in the Gaussian equivalence theorem. So if you want to see the derivation, please go to the paper. But this, as I said, this is a fixed point equation on scalar variables. So this is something you can easily solve, and then plot things like what is the generalization error, for instance, here as a function of, again, how many samples per dimension you have. And here is a case where the hidden submanifold has a dimension that is 10 times smaller than the ambient dimension, d over p 0.1. And the different curves are different values of the ridge regularization. So here, is a case where you see an interpolation peak, as you can see in number of other works in recent years in machine learning, and you see that this p goes away as you regularize, and then there is just an optimal value of the regularization and decay of the generalization error as you are getting more and more samples. So this is very, kind of the peak is standard now, and the behavior is intuitive here. On the heat map on the right, what you see is perhaps less intuitive, but also less easy to see. But what's interesting here is that when you actually from this picture read off what is the number of samples that you need to learn well, it's actually given by the dimension of the submanifold rather than by the ambient dimension. So even such a simple neural network without even hidden units is picking the fact that there is some latent dimensionality and structure to the data and is able to exploit it and is able to get a good generalization error as long as kind of the latent dimension is matched, not the ambient dimension is matched. So that's nice. Now I promised to mention the link to the random features, because those of you who have seen those papers by Montanari group, they were mostly on random features and comparing to mean field and NTK learning. So when you think about the definition of the hidden manifold model, you just reinterpret things a little bit. Now you say the C matrix is the data, is the input data. And the matrix F now will be the projections to higher dimensions as in the random feature learning. And the nonlinearity sigma is the nonlinearity that you apply when you learn with random features after the first layer. And then the labels are just generated as before by some teacher acting directly on the inputs. Then the same mathematical formula that analyzes the hidden manifold model actually gives you the performance of random feature learning in the same limit. This time it's a limit where the input dimension and the dimension of the space into you are projecting and the number of samples are all large and proportional to each other. And if you look at things this way, you can plot curves that are showing this double descent behavior. This time on the x-axis is not the number of samples as before. This time it is the width of the hidden layer. So as you are getting more and more parameters, the generalization error keeps decreasing. That is if you regularize, and if you don't regularize, you're seeing these interpolation peaks. Depending on which loss you are using, you may see the interpolation peak at 1 for the square loss, or at a transition where the data become or cease to be linearly separable for the logistic loss. That would be the red curve here. So you can kind of go into these things and play, with different losses and regularizations and see things like that. Or, the fact that the matrix F could be arbitrary, you can actually compare learning with random features, random Gaussian IID features, and subsampled Fourier matrix features. That will be the red ones. And you see that the subsampled Fourier is doing slightly better for the same width of the hidden layer. And this is actually something that has been observed before empirically in this paper, and probably a bunch of others that I didn't put here. So in this model, you can kind of put some theory on where this comes from. And finally, a question that you may be asking, I mean, definitely, we have been asking for a while, can we generalize these results to deep generative models? So far, I constructed the hidden manifold model by basically mimicking generator of GAN or decoder of autoencoder, but only one layer of the generator or one layer of the decoder. But to get kind of interestingly looking data, if you actually wanted to learn GAN on say, here I will have in a few slides, say if you wanted to learn a GAN on sci-fi, you need something with more layers and with convolutions, etc. So does the same theory apply for cases like that, where we would put more layers into the generator and ideally also learn the matrices in the layers? So that's the subject of this last paper that I want to present. So here is the setting. So as before, there will be some latent space in which the teacher is acting. So that will be represented, here in the lower part of the diagram is the teacher. The teacher is again some neural network with just few hidden units that is producing the labels. And then there is the generator that from the same latent space is using several layers, and they can be convolutional or have different structures, producing realistically looking images like the nice dog here. So that's the setting. And then the axes that are being generated and the labels that are being generated, it's a classical classification or regression task that is then being learned by a single hidden layer neural network, because more than that we so far cannot analyze. But can we put depth into the generator? That's the question of this paper. And the answer is that we can. And again, what makes this model still analyzable in the same sense is kind of a generalization of this Gaussian equivalence property, where we show that in the limit where the latent and input space dimension and the number of samples are all large with fixed ratios, and we show that the Gaussian equivalence still generalizes, and that the learning curve depends only on input correlation matrix omega here, and input and the latent variables correlation matrix phi here. And if the data were generated with these correlation matrices and were Gaussian, curve would be exactly the same. So that's the statement of this Gaussian equivalence property. In the deep case, we still don't have a full proof, but working on it. Proof is so far only for the shallow case, but empirically, I will be showing you that it's true. It's working. We just need to figure out how to prove it. And yeah, this is something very related to concurrent works by the group of Romain Couillet. So here I'm citing also their papers. I think it's not stated exactly the same way, but it's very, very related on the bottom line why what they are doing is working. So to give you an example of application of this, so here we took a deep convolutional GAN with random weights. So it's not as before IID because it's convolutional. So the weights are not IID, but the free variables that are there in the first experiment, we choose them at random. And this is some state-of-the-art network taken from previous work. with grateful to the authors that they shared with us all their trained networks and all that. And if you look on the random weights, the agreement between our theory for the stochastic gradient descent on this committee machine, which would be the full lines, and the crosses, which are actual experiments on the data generated from the generator and the labels generated by the teacher. Here we see completely perfect agreement on the generalization error, but that one has kind of a boring behavior, but also on some of these order parameters that have non-trivial behavior, and we capture it all. Now the question is, can we do more rather than using random weights for the free variables? Can we actually use the learned weights for the free variables? So here, this is where we take just the learned weights from the previous paper and then apply the same closed formula on that case, basically just computing from there the two empirical covariance matrices that I was mentioning on which the formula depends. And here we see, again, great agreement for the generalization error, some little deviations for some of the order parameters, but we actually think this is as a finite size problem as the input dimension in this network is quite small. So to get the empirical covariance matrix, we don't have it very precisely. But if we actually look at something like normalizing flows, which for our kind of purpose has the advantage that the input dimension is just the same as the ambient dimension, as the latent dimension, because it's an invertible neural network. So it's large in this case. So when we compute empirical covariances that are more precise, then we can again apply the same formula and we see perfect agreement. So yes, this kind of Gaussian equivalence property and these kind of formulas we have are applicable to deep generative models as well. And with this, I just go back to the list of references where you can read about that kind of research path we have of building solvable models for data that are closer to realistic data sets than the kind of naive teacher-student model. And with this, I want to open for questions and thank you for your attention.
Thanks so much, Lenka, for the great talk. So we have now some time for a few questions. If you're an attendee, please ask your questions in the Q&A. And if you're a panelist, just feel free to unmute yourself and ask the questions that you may have. So we have I'll start with a couple of questions that are already in the Q&A. So someone asked in the deep case, what if you could say a bit more about the manifold assumption, if what it means is that the latent variables lie in the low dimensional manifold, or if it's something else.
Yeah, so in the deep case, like we basically, like all that we are using about the manifold structure is the fact that the generative network, that we take from the two-sided papers just come in the form it comes. So in the case of the GAN, it just happens so that the GAN has input dimension that is much smaller than that the latent dimension is much smaller than the input dimension of the data. So it's in a sense that we are not doing any additional assumption. We just take the GAN as it comes. So it comes in the form of generating something that is only intrinsically having the dimension of the input into the GAN, which is much smaller than the output. So it's already there. We don't need to assume anything more. Of course, in the normalizing flow, the latent dimension is as big as the input dimension. So there we are not even really reducing it to a lower dimension manifold. So they're kind of, it's not that we are assuming it's just not there, but still the formula that we have is not assuming in any way that the dimension is actually small. It's, the dimension was small just in our motivation to design it this way. But in the formula, the dimension can be actually even larger than the input dimension. It holds for like whatever constant factor is between the two dimensions, and that factor can be smaller than 1 or bigger than 1. So we, in a sense, don't have to assume it in any way.
Thank you. So there's quite a few more questions. Let me see. So I wanted to ask you, so when you have the teacher-student models, is there any qualitative difference between when the teacher has exactly the same model as the student, or the teacher has a smaller model than the student? I mean, I guess the hidden manifold assumption is one such example where the teacher has a smaller model. But if I have, say, a teacher with a much smaller network, do you also see this thing where the students behave very differently on points outside of that small network,
so
whatever
if
this
you are
means?
so of course, I mean, once you start mismatching the student from the teacher, then you have so many options that it is like hard to say that there is no way to do it so that we reproduce this behavior. Like, we don't have a proof of that, like, but it definitely in the kind of things that come to your mind that you try, you don't see that behavior. It's not about like perfectly that the student needs to be matching perfectly the teacher. We of course tried like adding noise to the labels, mismatching the number of hidden units in the layers, mismatching the nonlinearity function between the teacher and between the student. And with these things, you don't reproduce that to student behavior. Which of course doesn't mean there is not a way to do it differently. In a sense, the Gaussian equivalence principle is telling you that, you know, if you like in a tricky way match the covariances, that you should be able to do that. But kind of naturally, you don't get it.
Okay, thank you. So we have time, I think, for only one more question. So I'll try to merge a few. So yeah, let's see. So I guess there's a question all about some form of a finite sample on an asymptotic bound. So I guess one part of this question is, can some kind of perturbation argument be used to make the Gaussian equivalence get some control, some non-asymptotic control on the risk? And I guess a related question, how do the double descent curves actually compare with empirical ones, right, on sort of non-asymptotic examples?
Yes. So one important thing is to say that when the asymptotics that we are considering here is not the usual asymptotics, right? It's not that the dimension is fixed and the number of samples goes to infinity. That would be kind of the statistics 100 asymptotics. Here the two are proportional. So the dimension is big and the number of samples is big. Now it is true that the theory holds in the limit, but all the figures that I have been showing when there were lines and points, the points were always empirical evaluation of actual training on actual like data set generated the way, you know, from the different models. And typically the sizes we are running there would be the dimension is 1000 and the number of samples is just alpha times that. So for those sizes, you get that perfect agreement with the asymptotic theory. So in a sense, for reasons that I'm not fully understanding, we are kind of lucky that the asymptotic theory kicks in at pretty small sizes of the 200s and thousands. Now, doing analytically some kind of finite size corrections to that limit, that's a little challenging. It's not, you know, it's much harder than the kind of fixed dimension and not infinity but finite, you know, a lot of non-asymptotic statistics out there. But this limit, when both of them would be kind of finite and you still want to kind of converge to that asymptotic limit, of course there are works, but not so many. That's interesting but challenging. Like already the asymptotics are not so easy to prove. But fortunately for us, they kick on very early on. So if the dimension is 10, maybe not, but if it is, say, a few hundred, then, you know, the points lie on the curve and the theory is pretty predictive.